So for the UCM, uniform circular motion, where equal distances were traveled in equal amounts of time, we took the case of a horizontal circuit and a mass A which was fixed. How come? I'm not going to discuss that. I didn't discuss that before, but there is a string in which there is an amount of tension, and then going in the positive anti-clockwise or counterclockwise direction, the uniform circular motion is taking place with equal angles traversed in equal intervals of time, which I have discussed in the previous lecture. Now today, and at this time, what we are going to discuss is, I draw another circle where instead of taking this situation, I am taking RT. This is the displacement vector at time t, and after a certain time delta t that has elapsed, the vector takes this direction. Okay, and it has traversed an angle of delta theta as per the diagram which I have made, and there is a change in the displacement of the vector, and that is delta r. Of course, the velocity at this moment, as you can see, which I have shown over here, is at an angle of 90 degrees to the to the displacement which we have at point A. And similarly, it will be there again, making an angle of 90 degrees with this as it goes at the point B. So I write the equation. It's very simple, just like what they also call triangle law of vector addition, but I'll call it head to tail. The head to tail method, tail to head method, which shows that this vector plus this vector is equal to this vector, which I have just shown here. The displacement vector r at a time t plus delta theta is equal to RT plus delta r. Now we found, and we are again putting the result that this omega is equal to delta theta upon delta t. As I again come back to the same situation, that delta theta, the change in the value of theta, is directly proportional to the change in time, and delta theta becomes equal to omega delta t. In the last lecture, I did show that the relation is a straight line on the time and theta axis. Okay, so I get this value omega delta theta upon delta t. Now I have the, look here, I have a triangle OABO. Okay, often we call it OAB. Khalas. So there are two angles. One is this angle here, and there is another internal angle over here. Okay. So in any situation of any triangle, we know that the sum sigma internal angles of any triangle is equal to pi radians or 180 degrees. This is a very well known fact from our junior classes. So taking advantage of this relation, we try to find out as to what the value of this is. Number 2, this is r, this one is r, and this one is also r. The distance from the center to the circumference. These two are equal, and therefore this becomes an isosceles type of a triangle. And now I say that these two will be, because they these two angles will be equal to each other, which I have shown over here, magnitude wise. Okay, we're just talking, being careful, saying that magnitude wise the angle OAB and the angle OBA will be equal to each other, which will turn out to be equal to pi minus delta theta. This plus this is equal to, plus this is equal to pi, and therefore this angle becomes equal to pi minus delta theta divided by 2. Okay, so which I can write, substituting the value from here, that angle OAB or angle OBA, this angle or this angle becomes equal to pi minus omega delta t divided by 2. Or separating the terms, it is pi by 2 minus omega delta t divided by 2. Now look here, if we consider this result, so what happens when delta t tends to 0? As delta t tends to 0, so this value turns out to be approximately equal to 0, and therefore this angle turns out to be approximately pi by 2. This is what I have tried to explain to you here, that as delta t tends to 0, so delta theta tends to 0. So this here, the arc AB, okay, the AB becomes tangential to OA. That is, the angle between the two becomes equal to 90 degrees. So this, in the limit that delta t tends to 0, this angle over here becomes approximately equal to 90 degrees, which means that the delta here, that is almost perpendicular. Arc AB is equal to radius into angle. So R, capital R, which is the radius of the circle, multiplied by delta theta, so that the velocity cap, the direction of the velocity vector is tangential to the vector at A, the displacement vector at A. So there is a 90 degrees lead, which we will discuss shortly, and as delta t tends to 0, the arc becomes approximately equal to the chord, and therefore the chord AB is equal to r delta theta, and we arrive at a result that the magnitude of delta r is equal to r, which is fixed, which is in the definition of the system, which we call the circle, into delta theta. Okay, so we establish that the mod of this delta r is equal to r delta theta. Now if I divide this delta r by delta t and this right hand side also by delta t, so what we will get is delta r upon delta theta is equal to r delta theta upon delta t, will be defined as the average speed Vt, which we take as v. And if so, substituting this, then this value becomes equal to v r omega, because r, the linear velocity, is equal to radius into the angular velocity radius of the circle into the angular velocity omega. Or I can write from this expression, I can obtain omega is equal to v upon r per second, or radian per second. Now the next item that I take up is centripetal acceleration, and I draw this circle again. This one becomes r1, this is r2, okay, and this is delta theta, and as I took here, so there is the delta r. And see here, what is interesting and what you can see for this, O is the origin and R is the radius, doesn't matter. What matters is that at the point A there is a velocity vector corresponding to that R1, and that is V1. And what do you find? What is the relation between the vector over here and the vector over here? That you can see vividly that there is an angle of 90 degrees, and the same thing exists over here, that an angle of 90 degrees exists, and this I have redrawn in the form of a transformation of things. Okay, so instead of A I am taking the point A dash, and instead of B I am taking the point B prime, B dash. So we find that the velocity over here is equal to V1 and the velocity over here is equal to V2, so that this gives the difference of the two velocities and we will get delta V. So if I substitute the things, I just establish that the value of vector R1 is equal to the value of vector R2, the two and is equal to R. However, the values are the same, okay, but the directions are different. The directions change, and that is the beauty of this uniform circular motion. So I can write R1 plus delta R is equal to R2, or delta R is equal to R2 minus R1, which is equal to AB. Okay, here I can show that the AB is the vector here. The AB is the vector over here. Okay, with the red ink. So this is AB, and when delta t tends to 0, then we write that the velocity at a time t is equal to, in the limit that delta t tends to 0, delta r divided by delta t, which will be in the form of the differential, the rate of change of r with time. So for UCM, the position vector RT rotates with a constant angular velocity omega, and so does the velocity vector. It also rotates continually with the same velocity vector, continually with the same frequency, the angular velocity omega. However, as I told you that my velocity is 90 degrees ahead of, the velocity is 90 degrees ahead of the displacement. So it's like this. If this is my velocity vector, then I have here, this is the velocity vector, this is the displacement vector, and if I just extend it here, you can see that there is an angle of 90 degrees by which the vector V leads. Okay, so let us go back to this set of figures and concentrate on this one between the velocities and the new origin O dash, A dash and B dash, which is akin to OAB, etc., which you have done earlier. So I can write in a similar fashion that the vector O dash B dash, which represents the velocity V2, can be written as equal to this vector plus from the head to this place, and this vector plus this vector gives the vector V2 according to the triangle law, also according to the tail to head way of adding vectors, which simply gives us the vector V2 is equal to vector v1 plus the change in the value of the velocity delta v. Change in the value of velocity is delta v. Now by definition we know that the average velocity of average acceleration is defined as delta v upon delta t, which can turn out to be equal to the v2 minus v1 upon t2 minus t1, where these corresponding times we take as t1 and t2 respectively. Okay, so this is the average velocity, and the instantaneous acceleration. This is the average acceleration. Instantaneous acceleration we take, look here, this is instantaneous acceleration as vector will be defined as, in the limiting case that delta t tends to 0, it becomes vanishingly small, delta v upon delta t, which we can define as the rate of change of velocity at the given instant of time. Like in the case of linear motion, we again have this expression. The only thing is that the new this thing is that it is also perpendicular to the velocity in the same way as the velocity was perpendicular to the value r or displacement. I told you that the velocity and the relation between the two of them is that if this is the displacement, then the velocity is at an angle of 90 degrees ahead of it, so leads it by 90 degrees. In a similar fashion, we find, and I'll just tell you how come the acceleration and the displacement, the velocity and the acceleration are in the same plane. The acceleration leads the velocity vector. So I just showed you how come this happens, and it's easy to realize that I can say that this is my r vector, r, and from here I have to do it, but what I do is that I change the initial position of this vector, and I say that this vector is my vector r. Try to understand that. Now the vector at this point that we have for the velocity vector, this goes 90 degrees ahead of this vector. So there is a vector r and there is a vector v. Now this vector, acceleration vector, is ahead of the velocity vector by another 90 degrees, and therefore what I am going to get in this case is that by acceleration vector, I am just displacing it a little bit on so that it can be seen by you easily and appreciated. Then this vector is the acceleration vector. So you can see this is radially outwards and this one is radially inwards, and of course the velocity vector is tangential to the path of the particle, the body, the mass under uniform circular motion. So the relation that we obtain, delta r upon r is equal to delta v upon v. If I divide both the sides throughout by delta t, I'll get 1 upon r, delta r upon delta t is equal to 1 upon v delta v upon delta r, which in the limit that delta t tends to 0 will turn out to be equal to 1 upon r ddt of r, rate of change of r, plus 1 upon v into dv dt, that is rate of change of v. But dr dt here, dr dt is equal to v and dv dt is equal to a as per their definitions. So I can write therefore this equation as V upon R, this side, is equal to A upon V, the other side. And then rearranging the terms, I'll get A is equal to V square upon R, okay, which is the centripetal acceleration. I will talk more about it later on. But my velocity is also equal to R into omega, okay. Therefore, I can write this equation again as A is equal to V square upon R, and therefore R is square, omega is square upon R, which becomes equal to R into omega square, which I do a little bit of jugglery with mathematics and write this expression R omega square as R omega multiplied by omega. R omega, of course, is equal to V, so I can write this equation as V into omega here, and then my A will become equal to, because it's like this, omega into V. I write it not as V omega because that's not musical, so it should turn out to be musical. It should, because music is what we can remember more as compared to noise. Anything which is not music is noise. So I say that the acceleration in this case, which has been shown over here, this is equal to the angular velocity times the velocity. Of course, this is an expression for, these expressions are for the magnitude of the acceleration. So you see, in this lecture we have talked about the we have done the physics of the uniform circular motion. We have obtained the expressions for and we have seen that the velocity vector is leading the displacement vector by 90 degrees, and this in turn, the acceleration leads the velocity vector by 90 degrees. So the interesting part is that the relation between the acceleration and R, A and R, is that this is 180 degrees R pi radians, which means the two are out of phase with each other, okay. So this is the kind of equation that we write. The acceleration is proportional to the displacement in the relation d2 psi upon dt2, which is the acceleration, is proportional to psi and is equal to some constant times, which is omega square is equal to minus omega square, or a constant, into psi. And this is the relation, this is the beautiful relation that we use in the explanation of simple harmonic motion, the harmonic motion, where the acceleration is proportional to the displacement itself and they oppose each other. If the opposition is not there, then we will not be able to get the beautiful equations that we obtain to simple harmonic motion. So when we discuss simple harmonic motion, so this kind of a relationship, you must understand that I've just extended this arc on this side and then seen that the velocity vector is leading and the acceleration vector is this thing. So this is center seeking or centripetal. So this acceleration A, which is written as V square upon R, A is equal to V square upon R. This is centripetal. We return with a little bit of more discussion and we'll take up a a few problems centripetal, which means center seeking, and the R, this vector is radially outside. This one is tangential. I've shown it to be tangential over here, and then I have not shown so far, but I'm going to show to you that at this instant of time I have the acceleration over here towards the center, the displacement is away from the center, and that the velocity vector is tangential to this vector, and makes this acceleration makes an angle of 90 degrees. So thank you for being with me. We return.